Good day, ladies and gentlemen. On our previous lessons, I introduced the work. So today we are going to focus on energy. The lesson is presented by me, of course, Mvakari KF. So we are going to start with the work energy theorem. So what is the work energy theorem? The work energy theorem is defined as the net work done on an object is equal to the change in object's kinetic energy. So as we all know that when the object is moving, it possesses what? It possesses kinetic energy. So in this case, the change in kinetic energy will be equal to the work net, the net work done on an object. This is given by the formula there. Work net is equal to the change in kinetic energy, where change in kinetic energy is kinetic energy after, which is the final kinetic energy, minus kinetic energy before, which is the initial kinetic energy. But we know from the previous grades that kinetic energy is given by this formula: half mass velocity squared, or this can be speed or velocity squared. Okay, so therefore the work net, the net work done, is gonna be equal to half the mass Vf from EKF minus kinetic energy initial, which is half mvi squared. So the net work done, where work net, it's in joules, where m is the mass of an object in kilograms kg. The final velocity, it is in meters per second, and the vi, which is the initial velocity, it is in meters per second as well. I have an example there, so let us do example 1. A little wagon with a mass of 2.5 kg moves in a straight line on a frictionless horizontal surface. It has an initial velocity of 3 meters per second, and it is then pushed 4 meters by a force with a magnitude of 2.5 newtons in the direction of the initial velocity. Use the work energy theorem to calculate the wagon's final velocity. So the instruction is very clear, good people. Here they're saying use the work energy theorem to calculate the wagon's final velocity. Okay, so this is a frictionless surface, as we can pick it up from the statement. Now it is pushed with a force of 2.5 newtons and it covers a displacement of 4 meters. So they say we should use the work energy theorem. What is the work energy theorem? Work energy theorem is work net is equals to the change in EK, okay, which is what? Which is EK final minus EK initial, okay, which then gives us what? This is work net. This is also work net, which then gives us half mvf squared minus half mvi squared. So we have there is only one force that is acting on this wagon, which is the force applied. There's no other force. So the work net is just going to be what? The work that is done by the applied force. So this now we are going to have what to call work applied is equals to what you call half mvf squared minus half mvi squared. So the work applied is going to be the force applied multiplied by what? By changing x. Cos of theta is going to be equals to half mvf squared minus half mvi squared. Okay, so the force applied is how much? The force applied is 2,5. Okay, 2,5 newtons, and the displacement is what? It's 4 meters, and then it is in the same direction as what? As the displacement. This is going to be cos 0 degrees, which is equals to half. What is the mass of the wagon? The mass of the wagon is given there as 2,5 kg. So this is going to be 2,5. We are looking for the final velocity. Okay, minus half into 2,5 into the initial velocity is what? The initial velocity is 3, which is 3 squared. Okay, so the unknown here, what we're looking for, we've got only one unknown, which is vf. We're looking for vf, and it seems like I'm running out of space here, so I will have to put another page underneath here, okay, so that I can continue with this. So what do we have? This is going to be 2,5 multiplied by 4 cos of 0. This is going to be to give us 10. So we're gonna have 10, which is going to be equals to half of 2,5, 0,5 times 2,5. This gives us 1,25. This is going to be 1,25 vf squared minus 0,5 multiplied by 2,5 3 squared. Okay, so this is gonna give us 11,25. so this is gonna be 11,25. so we transpose this to the other side. So what are we going to have? We are going to have 10 plus 11,25, which is equals to 1,25 vf squared. Okay, because we transpose this one to the other side. So plus 10, so this is going to be 21,25 is equals to 1,25 vf squared. We divide both sides by 1,25. This cancels that, so we're going to have vf squared divided by 1,25 is equals to 17. So vf squared equals to 17. So and then after that we introduce the square root on both sides. Introduce the square root, so this will cancel that, and then we have vf, which is equals to here is going to be plus or minus, okay, the square root of 17, the square root of I'm having a problem with the square root here. Now the square root, okay, let us use this, the square root of 17 halves. The square root of 17 is going to be 4 plus or minus 4,1 2 meters per second. So vf is going to be 4,12 meters per second. So this is going to be our final velocity, and we used what? We used the work energy theorem. Under the work net, there's only one force that is acting on this object, which is the applied force, which was 2,5. Okay, now let us do example 2. We are still on what? We are still on energy. We are still doing energy. What do we have here? A worker pulls a grate of mass 30 kg from rest along a horizontal floor by applying a constant force of magnitude 50 Newton at an angle of 30 degrees to the horizontal. A frictional force of magnitude 20 Newton acts on the grate whilst moving along the floor. So whatever that is being said here is represented on this what you call diagram. The first question is calculate the net work done on the grate as it reaches point P 6 meters from point O, from here to there. Okay, so we are asked to calculate what? The net work. So for number 1, the work net is going to be equal to, now what do we have in this case? We've got the applied force. Okay, we also have the frictional force. So there are two forces that are acting on this object. So this is going to be the work applied plus the work done by the frictional force. So this is going to be the applied force, change in x cos of theta, plus the frictional force, what? Change in x cos of theta. So what are we going to have? So the applied force is 50 newtons. Now the displacement is 6 meters, but now the angle between the displacement and the force, it is 30 degrees. So this is going to be cos of 30 degrees plus what is the magnitude of the frictional force? 20 newtons times 6, which is the displacement, cos of. Now since we know that the frictional force opposes the motion, so the frictional force it is in that direction, okay, whereas the displacement is this one. So the angle between the displacement and the frictional force is 180 degrees. So this is going to be 180 degrees. What do we get? So this is going to be 50 times 6 cos 30 plus 20 times 6 multiplied by cos of 180. We get how much? We get 139,81. if we round off to 2 decimal places. What is the unit? The unit is joules. So this is going to be what? This is going to be the work net. Calculate the network done on the grate. Okay, number 2, use work energy theorem to calculate the speed of the grate at the instant it reaches point P, which is the final speed. So we are asked to calculate the final speed. So using the work energy theorem, we know that work net is equals to the change in EK, okay, which is equals to half mvf squared minus half mvi squared. Okay, now what is work net? We calculated work net on number 1, so we can just substitute there 139,81 is equals to half. What is the mass? The mass is 30 kg. The 30. Okay, we are looking for vf squared minus half. What is the mass? The mass is 30 and then the initial velocity. Now with the initial velocity, we're told that it is from rest. So the initial velocity is 0. It's going to be 0 squared. Okay, so we're gonna have 139,81, which is equals to the half of 30 is going to be 15 VF squared minus this is 0 there. Okay, so we have 139,81 15 VF squared. So we divide both sides by 15. Divide by 15, divide by 15, this cancels that. VF squared is equals to divide by 15, we get 9,32. So this is going to be 9,32, and we introduce square root on both sides. Introduce square root, we introduce square root, this cancels that. VF is going to be equal to answer 1/2. This is going to be 3,05 plus or minus, okay, plus or minus meters per second, but the correct one is the positive one. So VF is going to be equals to 3,05 meters per second. So good people, we managed to calculate the final velocity at point P using what? Using the work energy theorem. Okay, don't forget that in this case we had more than one force acting on the object, okay, which was the applied force and the frictional force. So the work done by the applied force was this one, and the work done by the frictional force was this one. So when adding the two, what do we get? We get the work net. So with this work net, we can use this work net on what? On the work energy theorem to calculate what? The final velocity. That is the end of my lesson. Hope you understand. Thank you.